What if everything we can see, the stars, the galaxies, even our own hands, is just the faintest glimmer of reality? Picture the universe as an iceberg floating in an endless cosmic ocean. The tip, the part we can observe, makes up a mere 5% of all existence. The rest, a vast, invisible realm of dark matter and dark energy, two forces so mysterious they defy everything we thought we knew about physics. This isn't science fiction, it's the startling truth astronomers grapple with every day. And here's the real kicker: these hidden forces might be intertwined in ways that could rewrite the very laws of nature. Think about that for a moment. Every telescope, every satellite, every experiment humanity has ever conducted has only scratched the surface of reality. Dark matter, the unseen scaffolding that holds galaxies together, and dark energy, the mysterious force accelerating the universe's expansion, aren't just curiosities, they're the dominant players in the cosmos. Yet we can't see them, touch them, or even fully comprehend them. It's like trying to describe a symphony by only hearing the faintest echo. This duality, dark matter's pull versus dark energy's push, has left scientists both baffled and exhilarated. What if these two forces aren't separate at all? What if they're two sides of the same cosmic coin, dancing in a hidden dimension we're only beginning to glimpse? That's the journey we're embarking on today. Over the next 40 paradigm-shifting insights, we'll peel back the layers of this cosmic enigma, exploring cutting-edge theories, mind-bending experiments, and the philosophical questions that arise when we confront the limits of human knowledge. From the deepest voids of space to the most advanced laboratories on Earth, we'll uncover how dark matter and dark energy might shape everything from the fate of the universe to the very fabric of reality itself. This isn't just about science, it's about redefining what's possible. So buckle up. By the end of this exploration, the universe will look nothing like what you thought it was. Galaxies should fly apart. That's the startling truth Vera Rubin uncovered when she studied their rotation in the 1970s. Stars on the outer edges of spiral galaxies move so fast that the gravity from all their visible matter, stars, gas, dust, shouldn't be enough to hold them together. Yet they don't escape. Something invisible, something far more massive than anything we can see, must be anchoring them in place. That something is dark matter, an enigmatic substance that doesn't emit, absorb, or reflect light, yet exerts a gravitational pull strong enough to sculpt the universe itself. Take the Bullet Cluster, one of the most striking pieces of evidence for dark matter's existence. When two galaxy clusters collided, their visible matter hot gas glowing in X-rays slammed together and slowed down like cars in a cosmic traffic jam. But something else kept moving ahead, undisturbed. The gravitational lensing effect revealed massive, invisible clumps passing right through the collision, dragging space-time with them. That invisible mass, dark matter, completely detached from ordinary matter, yet holding entire galaxies in its ghostly grip. But here's where the mystery deepens. While dark matter pulls the universe together, dark energy does the opposite, pushing it apart at an accelerating rate. Imagine a cosmic tug of war where one team is invisible and the other is undetectable. Dark matter's gravity binds galaxies into vast webs, while dark energy stretches the very fabric of space between them. And somehow, these two opposing forces have been locked in this dance for billions of years, shaping everything from the largest structures in the cosmos to the fate of the universe itself. What's even more mind-bending, we still don't know if they're separate phenomena or two faces of the same deeper, darker truth. For centuries, scientists assumed the universe's expansion was slowing down. that gravity, the great cosmic glue, would eventually pull everything back together. Then in 1998, two separate teams studying distant supernova made a discovery so shocking it earned them the Nobel Prize. The universe wasn't just expanding, it was accelerating, as if some invisible hand had pressed down on the cosmic gas pedal. This wasn't just unexpected, it shattered our understanding of physics. The culprit, dark energy, a mysterious force that makes up about 68% of the universe and behaves like anti-gravity, stretching space itself apart faster and faster. Picture a balloon inflating, but instead of slowing as it grows, the rubber stretches faster with each passing second. That's dark energy in action, a repulsive force embedded in the vacuum of space, growing stronger as the universe expands. What's truly bizarre is that Einstein almost predicted this a century ago with his cosmological constant, a mathematical fudge factor he added to general relativity to keep the universe static. He later called it his greatest blunder when Edwin Hubble proved the universe was expanding, but now it turns out Einstein might have been right after all, just for reasons he never imagined. The evidence came from Type 1, a supernova, the cosmic lighthouses astronomers used to measure vast distances. These dying stars explode with such consistent brightness that any variations in their observed light reveal how fast space is stretching. When researchers compared nearby supernova to those billions of light years away, they found the distant ones were dimmer than expected, meaning space had expanded more than gravity alone could explain. The only possible conclusion, something was overpowering gravity's pull, and we'd been blind to it until now. This revelation set up the ultimate cosmic showdown. On one side, dark matter's relentless gravity, pulling galaxies into clusters and weaving the universe's large-scale structure. On the other, dark energy's repulsive push, driving galaxies apart so fiercely that in trillions of years, distant galaxies may vanish beyond an unreachable horizon. It's a battle between construction and destruction, with the fate of everything hanging in the balance. And here's the twist: we still don't know whether dark energy is constant, as Einstein's cosmological constant suggested, or if it's evolving, growing stronger or weaker over time. The answer could determine whether the universe ends in a cold, lonely fade or a violent rip apart at the seams. If you could see the universe on its grandest scale, it wouldn't look like a random scattering of galaxies. It would resemble a spider's web, glowing with threads of light stretching billions of light years across the cosmos. But here's the catch: that entire structure, the so-called cosmic web, is built on something we can't see. Dark matter acts as the invisible architect, weaving galaxies into vast filaments that intersect at dense nodes like celestial metropolises. These filaments aren't just empty lines, they're highways of gravity, funneling galaxies toward one another over eons, while the voids between them grow ever larger, stretched thin by dark energy's relentless push. Modern supercomputer simulations reveal this hidden architecture in stunning detail. Run the clock backward, and you'd watch galaxies retreat along these dark matter threads, like beads sliding back onto a string. Speed time forward, and you'd witness dark energy's eerie influence, the voids expanding, the web stretching, as if the universe itself is being pulled apart at the seams. The Sloan Digital Sky Survey captured this duality in action, mapping millions of galaxies to expose the web's intricate patterns. But the real shock came when researchers compared these maps to the cosmic microwave background, the afterglow of the Big Bang. The slight temperature variations in that ancient light aligned perfectly with the web's filaments, proving dark matter had been shaping the universe since its infancy. This creates a profound paradox. Dark matter's gravity is the ultimate cosmic sculptor, pulling matter together to form galaxies, clusters, and the web itself. Yet dark energy works in opposition, accelerating the expansion of space between these structures, isolating them in growing voids of near nothingness. It's as if the universe has two competing voices, one whispering come together, the other shouting fly apart, and the balance between them dictates everything. In the early universe, dark matter dominated, forging the cosmic web we see today. But as expansion accelerated, dark energy took the lead, and now it's reshaping the future. Billions of years from now, distant galaxies may be so far-flung that their light will never reach us, leaving future civilizations with a sky nearly empty of stars. What's even more startling, this tug-of-war might not be a coincidence. Some theorists suggest dark matter and dark energy could be manifestations of a single, deeper phenomenon, a unified, dark sector operating by rules we haven't yet uncovered. Imagine if the force that builds galaxies and the force that tears them apart were two sides of the same cosmic coin, shifting dominance as the universe evolves. That's the kind of revelation that could rewrite physics textbooks. Until then, we're left watching the web's threads stretch ever thinner, wondering if we're witnessing the universe's construction or its slow unraveling. Let's talk about the cosmic pie chart, a slice so absurd it makes even seasoned physicists pause. Imagine cutting a pizza where just one tiny sliver, a mere 5%, is the stuff you recognize: planets, stars, your morning coffee. The rest, 27%, is an invisible, intangible substance we call dark matter, and a whopping 68% is dark energy, a force so baffling it makes the universe expand faster against gravity's pull. Together, these two dark components make up 95% of reality, leaving everything we've ever touched, seen, or studied as cosmic afterthoughts. This isn't just a minor accounting error, it's a full-blown revolution in physics. Classical theories, from Newton's gravity to Einstein's relativity, were built on the assumption that what we see is what's there. But now, we're forced to admit that the visible universe is barely the tip of the iceberg. As physicist Brian Greene put it, we're like goldfish swimming in a pond, utterly unaware of the water surrounding us. Our equations, our telescopes, even our intuition, they're all tuned to that 5%, leaving us blind to the true nature of reality. Consider how this shakes the foundations of science. For centuries, we've relied on light to understand the cosmos. Stars emit photons, telescopes collect them, and our brains piece together the story. But dark matter doesn't play by those rules. It doesn't glow, absorb, or reflect light. It's a ghost that only betrays its presence through gravity's tug. And dark energy, it's even more elusive, a property of empty space itself that defies everything we know about attraction and repulsion. This imbalance isn't just a curiosity, it's a crisis. If 95% of the universe is invisible and unexplained, then our most fundamental theories are incomplete. It's like trying to predict the weather by only studying raindrops while ignoring the wind and the sun. The hunt for these missing pieces isn't just about filling gaps, it's about rewriting the rules of existence. And that brings us to the next challenge. How do you detect something that refuses to be seen? Deep beneath the Black Hills of South Dakota, in a former gold mine turned into a cutting-edge laboratory, scientists are hunting for ghosts. Not the kind from campfire stories. These ghosts are particles of dark matter, streaming through Earth by the trillions every second without leaving a trace. The LUX Zeppelin experiment, shielded under 1.5 kilometers of rock to block cosmic interference, waits patiently for the rarest of events, a dark matter particle bumping into an atom of liquid xenon. The detector's ultra-pure xenon tank, chilled to -100 degrees Celsius, is so sensitive it could spot a single photon flashing from such a collision. Yet, after years of searching, the dark matter particles, if they're even there, remain stubbornly silent. This isn't just a technical challenge, it's a cosmic game of hide and seek with the universe's most abundant yet elusive substance. Theorists have two leading suspects for dark matter's identity: WIMP and actions. WIMP, or weakly interacting massive particles, are heavy, slow-moving candidates that would reveal themselves through rare collisions with ordinary matter. Actions, on the other hand, are feather-light particles theorized to convert into photons in strong magnetic fields. Experiments like ADMCS in Washington state use powerful magnets and ultra-sensitive detectors to listen for this faint whisper of conversion. But so far, neither approach has yielded definitive proof. The frustration is palpable. Imagine trying to catch smoke with your bare hands. That's the scale of the challenge. And dark energy, it's even more slippery. Unlike dark matter, which at least tugs on galaxies, dark energy leaves no local fingerprints. Its presence is only measurable through the universe's accelerating expansion, like tracking the stretch marks on space-time itself. The most precise measurements come from observatories like the Dark Energy Survey and the upcoming Euclid Space Telescope, mapping billions of galaxies to trace how dark energy's push has evolved over cosmic history. Yet, for all their elusiveness, these dark components have sparked theoretical revolutions. Some physicists now speculate that dark matter and dark energy might not be particles or fields at all, but signatures of gravity behaving differently on cosmic scales. Modified Newtonian dynamics, or MUND, suggests tweaking gravity's equations could eliminate the need for dark matter entirely, though it struggles to explain phenomena like the bullet cluster. Others propose dark energy could be a dynamic quintessence field, changing strength over time. The boldest ideas venture into extra dimensions or holographic universes, where our reality is just a shadow of deeper, darker processes. What's clear is this: every null result, every unexplained anomaly, is pushing us toward a physics revolution. The experiments may seem like shots in the dark, but they're the only way to illuminate a universe that's 95% invisible. And when, not if we finally detect these shadows, the discovery will redefine not just cosmology, but our very place in the cosmos. What if dark matter doesn't exist, and the real problem is our understanding of gravity itself? That's the radical proposition behind modified Newtonian dynamics, or MUND, a theory that dares to rewrite one of physics' most sacred laws. Instead of invoking invisible matter to explain galaxy rotations, MUND suggests gravity doesn't weaken as quickly over vast distances as Newton or Einstein predicted. Picture a car that mysteriously speeds up when you take your foot off the gas. That's how MUND interprets the motion of stars at the edges of galaxies. No dark matter required, just a subtle tweak to gravity's rulebook. The idea isn't without merit. MUND accurately predicts the rotation curves of many galaxies using just their visible mass, a feat that impressed even skeptical astronomers. But the theory hits a wall when faced with cosmic collisions like the bullet cluster, where gravity's effects clearly separate from visible matter. Proponents argue MUND might still explain these anomalies with additional refinements, but critics see it as a patchwork fix, like adding epicycles to the old Earth-centered model of the solar system. The debate grew fiercer when the James Webb Space Telescope spotted ancient galaxies that appear too massive and too structured to exist in a MUND-dominated early universe. These galaxies, seen as they were just a few 100 million years after the Big Bang, challenge the timeline of structure formation unless dark matter's gravitational scaffolding was already in place. Dark energy, however, resists such alternative explanations. No modification of gravity has yet accounted for the universe's accelerating expansion without invoking some form of energy inherent to space itself. Wildman tackles galaxy-scale oddities. Dark energy operates on a cosmic scale, stretching the very fabric of reality. Einstein's cosmological constant remains the simplest explanation, but even that feels like a placeholder, a mathematical shrug in the face of profound ignorance. Some theorists propose dark energy could be a dynamic field, evolving over time, while others speculate it's a symptom of extra dimensions leaking into our universe. The tension between these approaches reveals a deeper truth. Our models of the cosmos are incomplete, whether we tweak gravity or embrace the dark side. Man challenges us to question long-held assumptions, but its struggles with large-scale observations suggest dark matter's pull is real. Meanwhile, dark energy's repulsive force defies any straightforward fix, leaving physicists to wonder if both phenomena hint at a grander theory waiting to be discovered. The takeaway: sometimes the universe's greatest mysteries aren't just about finding answers, they're about learning which questions we've been asking wrong all along. Empty space isn't really